Let's move on to the second speaker. So I would like to warmly invite Dr. Tijana Markovic to deliver her talk. So let me give a brief introduction about Tijana. So she's a researcher at the University of Portsmouth, United Kingdom. Her research focused on applied artificial intelligence with a particular emphasis on cybersecurity, federated learning, and privacy-preserving machine learning. She has more than a decade of teaching experience in computer science at both undergraduate and postgraduate levels. She has participated in numerous national and international research and innovation projects, working closely with academic institutions, industry partners, and public sector organizations to address real-world cybersecurity challenges. Her current research explores trustworthy AI methods for cybersecurity with a focus on secure collaborative learning and network intrusion detection. So over to you, Tijana.
Hello, can you hear me? Okay, sounds good. Thank you very much for the introduction. So as I was already introduced, so my name is Tijana Markovic. I'm coming from the University of Portsmouth in the United Kingdom. And the title of today's talk is Privacy Preserving Federated Learning for Network Intrusion Detection. First of all, I would really like to thank you for inviting me here and to say that I'm really honored to be speaker today and I'm really enjoying Sri Lanka. So first of all, I will just give a brief introduction about myself. So as I already said, I'm currently working as a researcher at the University of Portsmouth in the United Kingdom, but I'm also visiting professor at the Faculty of Information Technologies, University Mediterranean in my home country, Montenegro. Before that, I worked as postdoctoral researcher at Mälardalen University in Sweden, and I was also visiting researcher at Center for Data Analytics and Biomedical Informatics in Temple University in the United States. Regarding my education, I have PhD in software engineering from University of Belgrade in Serbia, and as it was already mentioned, my research area is applied artificial intelligence with particular emphasis on cybersecurity. So today I will talk about network intrusion detection systems. So the goal of these systems is to detect malicious activities early and mitigate them promptly. So the idea is to use machine learning for this purpose. So basically we have a lot of data that are collected on the network, and we use this data to learn how we can distinguish between normal and anomalous behavior of the system of the network. So this is basically just a classification problem in machine learning. So we do either binary classification, so we try to distinguish between normal behavior or attack, and also we can do multi-class classification where we can try to also distinguish which type of anomaly or attack there was in the network. When we try to apply machine learning to this type of systems, there are different approaches that we can use. The most traditional and the most frequent one is centralized learning, where basically all the data from the network is sent to the central server, and machine learning and single machine learning model is trained there. This is a traditional approach that is not very popular anymore because of data privacy. So when all the nodes are required to share their data to a central server, that can raise various concerns regarding privacy and security of the data. That's why we are trying to propose other approaches that will enable us to keep data more secure. One additional approach is distributed learning, so where we have data partitioned across multiple nodes, and then we use them to jointly train a single model in parallel. And there is a federated learning where each node trains a local model on its own data. So only model updates are sent to the server to build a global model, so there is no data sharing. The topic of my today's presentation is a federated learning. So I will talk about my own research in this area. So the approach that I will present today is based on random forest. Why random forest? Because in various research, random forest is proved as one of the most efficient machine learning algorithms for network intrusion detection. Although it's traditional algorithm, it's not deep learning, but it's proved as very successful in this area. So in my research, I combine random forest with the horizontal federated learning. So here we have data sets that are on local nodes. And these data sets share the same feature structure, but they have different samples, which ideally fits to network intrusion detection problem, where each node has its own data and can work with its own data without need for data sharing. The goal of combining these two is to provide privacy-preserving network intrusion detection system. So how this works? So let's assume that we have n clients. So each client has its own data. Each client trains random forests on its own local data. And then these forests are sent for the aggregation on the server where we generate the global random forest model. After generating this global model, we send it back to clients for further use. How this aggregation is performed? So we proposed multiple options. So when we send all the random forests to the central server, we have a candidate pool. So that is all forests from all the clients. Then we decide which ranking criteria we will use. So we will use either accuracy or weighted accuracy. Then we have to decide which sorting method we will use. So we can use sorting per random forest, which means that we rank the decision trees independently within each random forest. And the other option is global sorting, where we put all decision trees together into a single candidate set, and then we rank them globally. After we decide which sorting we want to use and we sort the decision trees, we will pick the best top performing M trees that will be included in the global model. So this approach was further improved by adding the decentralization. So the idea is to provide decentralized federated learning, so to completely remove the need for a central aggregator server. So we, instead of using the server as an aggregator, we perform a peer-to-peer one-shot model aggregation scheme. So how this works? So basically we have first client that has its first random forest that is trained, and then later propagated to the second client. Second client now has a candidate pool that is composed of his own random forest and the previous random forest from the previous client. The aggregation strategy is performed, best trees are selected and propagated further. This is done further in peer-to-peer communication until the end. So at the last client, we have the candidate pool, we select the best trees, and we generate the final random forest model. So this is performed in one-shot aggregation, so there is no backward loop. We just perform it client to client, and at the end, the final random forest is used on all clients. So this is the same, all the aggregation methods are the same. The difference is that here we don't have a server, but we do that in peer-to-peer communication. In order to evaluate this approach, we use the existing datasets. The problem is that the most of existing datasets are tabular datasets, so where we have network data, pickup files that we transfer into tabular data, we have features and so on, but we don't have any idea from which nodes in the networks this data come. In order to simulate the data division, we decided to use a single feature and to use that as a division criteria. So based on single feature value, we split the data and distribute it on n clients depending on the specific feature. Datasets that we used are the most famous benchmark dataset in network intrusion detection area. So those are KDD99, NSL KDD, UNSW MB15, and CIC IDS 2017. So for this benchmark dataset, we use a specific feature to partition them. So for KDD and NSL KDD, we use the protocol, which resulted in 3 different subsets. For UNSW MB15, we use service feature, which resulted in 6 subsets. And for CIC, we use destination port, which resulted in 14 subsets. What you probably know about these data sets that, and you can see also from the name of the data set, that the latest one was in 2017, which is almost 10 years old data set. That's why we decided to include additional dataset, which is a more recent dataset called the Westermo Network Traffic Dataset that was generated in 2023. For this dataset, no additional partitioning was required because this dataset was collected from 3 different clients, and this information is kept in the dataset, so there is no need to perform additional artificial partitioning, but the data is already partitioned on 3 different clients, so we have 3 subsets by default. And in addition to this, we also decided to include a 5G dataset, that is 5G NIDD dataset that was generated in 2022. And this dataset was also partition based on the protocol feature, again resulting in 3 different subsets. To evaluate the proposed approach, we did 4 different experiments. So the first one was just the centralized random forest, just the regular random forest where we have all data together on the server. So the entire data set is available. We split it on training, validation, and testing. 70% we used to train the model, 10% we use to determine the best hyperparameters, and 20% we use to train the model. In the second experiment, we just use a local random forest. So we assume that the data sharing is not allowed. So each client is training based on its own data. And we use the best hyperparameters that we selected in the first experiment. We evaluate all local random forest on the entire test set from the first experiment. And we do that in all experiments in order to compare the results. So in third experiment, we do the centralized federation that I explained before. So local random forests that we got are aggregated into global random forest using the different aggregation strategies that I presented before, and again evaluated on the full test set. And for the fourth experiment, we do again federation, but now in decentralized way. So now we combine random forest model in sequential peer-to-peer manner using different aggregation strategies. In addition, and again, we evaluate on the full test set. In addition, in this experiment, we also evaluate how the ordering of the peers can affect the final results, because for the difference of the third experiment where the aggregation is performed in the server, here we perform it into peer-to-peer sequence. So we want to see, will that order matter in the final results? Now I can show you some of the results. So here you can see the results for centralized random forest. Then for the local random forest, since the number of clients is different between different data sets. So you can see that in the previous slides, you saw that a number of clients varies from 3 to 14. So in order to present these results, we decided to present 3 values. So for each data set, we present minimum, maximum, and average accuracy of local random forest, of the client random forest. Then you can see federated random forest. This is centralized federation, and you can see decentralized federated random forest. What we can conclude from this chart? So first of all, we can see, of course, that centralized random forest has the best performance, but that is only possible when the full data centralization is allowed. And in real applications, it's almost never allowed. So, but in ideal scenario, of course, data centralization is the best. Then if we compare other approaches, we can see that local random forests are not reliable because we can see very big differences between minimum, maximum, and average random forest on the client. This means when we have a heterogeneous data, it's very difficult for clients to make some global understanding of the problem only on the local data. And then if we look at the federated model, so centralized and decentralized one, we can see that the centralized one can outperform average client model on 5 of 6 datasets, but for decentralized one, we can see that it outperforms centralized federation. And what is also very important, that it can come close to centralized random forest, which means that with the decentralized federation, we can achieve same or very close performance to regular centralized model where we have an entire data set on the server. In addition to this, I want to show the results on peer ordering strategies. So what I explained before, that we want to see how order of the clients can affect these results. And here you have results for all 6 datasets. And what is very important to note here, that all strategies converge to similar final accuracy. So here we evaluated 3 different options. So we sorted clients based on training size, so based on the amount of data they have. Then we sorted them based on malicious ratio, so how many, which portion of their data is actually malicious. And finally, we did it randomly. So you can see that although in the first steps, they have very big differences in accuracy, until we complete the entire sequence, they all reach, let's say, same or similar accuracy. And this is very important because this means that final performance is not dependent on the specific ordering. This is also very important because this is additional privacy. There is additional privacy moment here, because if ordering was important, we would need to share information beforehand about the data. Since it's not important, there is no need for additional coordination step, and there is no need to share any information about local data. Clients are not required to tell each other how much data they have, what is the malicious ratio, and so on, which enables us to avoid to avoid sharing any information about the data set. For future work, we plan to explore how we can expand this one-shot model aggregation to do some iterative communication and to see can that improve model performance. Also, we would like to investigate more aggregation and tree selection mechanism, and also to see how this framework will react on unreliable client participation. Additionally, we would like to explore personalized federated learning settings, and also to evaluate this model on real hardware using an ENSURE-6G testbeds. For the end, I would like to thank to ENSURE-6G that supported this research. So the research that you saw today in my presentation was conducted during my secondment in Barcelona with Telefónica Innovation Digital, and it resulted in a paper that will be presented at ACML PKDD conference in September in Naples, in Italy. This paper was accepted last week. So that is joint work within ENSURE between University of Portsmouth and Telefónica. And we also plan to expand this research with the ideas that I presented for future work, and hopefully to test it on Telefónica and Montimage testbeds to see how it performs on real hardware. I think that's it from my side. I'm available for any questions that you have. And also, if you want to discuss this further, here is my email address. Thank you very much.
Thank you very much, Dr. Tijana. So